Hello, I'm Ayumi, who is a doctoral student in Tohoku University. In this work, me and co-authors investigate learning-free methods for place description and traversability analysis in unstructured environment. Place recognition, which recognizes visited places, is essential for any robotic applications. Detecting identical places enables map collection as well as localization in the existing map. In this work, we are interested to think place recognition in uneven terrain. Unstructured environments, such as planetary surfaces, pose a significant challenge for any kind of place recognition because of its visual and structural ambiguity. Moreover, robots must interpret incoming hazards for secure navigation. However, existing place recognition approaches do not simultaneously localize traversable areas, despite of its importance. This is because they quickly lose the physical property of the ground during the descriptor generation. In this work, we are motivated to solve place recognition and traversability analysis from the perspective of ground structure. Criteria we settle are as follows. First of all, the structural representation should be effective and informative enough to be deployed with limited computing resources. Secondly, the algorithm should interpret incoming hazards in a common principle, which realizes simultaneous safe navigation. We propose our approach, SDFT. This is inspired from our insight that aggregation of frequencies represent gentle ground curvature in much more informative way. Moreover, that operation is a common principle for traversability analysis. There are many structure-based approaches proposed to solve visual ambiguity. We first cite traditional local descriptors. They are computing normal vectors when describing local structures. GPGM-SLAM applied Gaussian process regression to reconstruct precise 3D representation and enables informative description. However, the process itself requires considerable computation. Global descriptors, which exploit a point cloud's appearance, can cope better with noisy point clouds. Approaches using LiDAR encodes the surrounding structure with high entropy descriptors. Deep learning approaches have also received considerable attention in the field of place recognition. Although these may significantly improve performances, they present high computational complexity in cases where GPUs or LiDARs are available. There are comparable global descriptors such as SHORT, SCD, and M2DP. However, we observed they become less informative in unstructured environments. Moreover, all of these do not solve simultaneous traversability analysis. Now, let's dive into methodology we propose. The proposed pipeline consists of following parts. Given a local point cloud generated from the camera, we first project it onto the frame defined by PCA process. As the normal vector is uniquely determined, resulting DEM becomes invariant with regard to the elevation of the submap's origin. Applying DFT operation to DEM, we gain its output utilized for the two tasks. For place recognition, the DFT output is fed into proposed sampling process, which enhances robustness against rotation. Resulting matrix A is inputted to SVD composition for dimensionality reduction. Meanwhile, the DFT output is jointly fed into iterative low-pass filtering, which analyzes traversability from the perspective of the ground's undulations. To form DFT data, we take the logarithm of all absolute values. Resulting DFT data represents the intensity of each frequency embedded in the ground structure. Considering DFT's characteristic, rotation in the spatial domain causes the same rotation in the frequency domain. Considering this, we must add some modification to it to gain robustness against rotation change along the normal. To mitigate this issue, we divide DFT output into polar beams and index them according to their radius and angle. From each beam, we take the maximum values to gain max pooling effects. As shown in this slide, values in beams of the same color are jointly max sampled to deal with opposite revisitation. To arrange kernel windows, the DFT output is unrolled in the log polar coordinate system. Our proposed method samples maximum values in each kernel window, and they are fed into SVD to be the final form of SDFT. Traversability is affected by various factors, including the kinematic model of the robot and the physical properties of the environment. This study, however, posits that terrains with finer undulations pose a greater risk to traversal. The aim of this part is to extract and localize the regions of the point cloud forming each frequency. To solve this, we adopt iterative low-pass filters, which deconstructs smoother point cloud and highlights points constituting the target frequencies by comparing heights. Aggregating points per frequency, we gain detailed cost map, which can be utilized for path planning. In this section, I will present experimental evaluation and its results. To simulate sequences in unstructured environment, we used publicly available datasets in planetary analogs called MADMAX LRNT and SGLI. To investigate its applicability in urban areas, we also applied an urban dataset. Evaluation metric we used is top K accuracy, which reflects recall rate among models' top K predictions. SHOT, M2DP, and STD are selected as compared methods to demonstrate the potential of SDFT. In evaluation, STD is separately evaluated from SHOT and M2DP because different experimental setups are required for fair comparison. As STD fails to generate valid descriptors when it cannot detect decent amounts of key points, we additionally set a new metric, stability. This denotes the ratio of frames in which STD succeeded in generating descriptors. In the below table, we list both methods' top 10 accuracy. Ours shows favorable performances in both environments. On the other hand, STD's performance significantly declines in unstructured environments because it relies on salient detections and fails to form informative representations. From now on, I introduce evaluation compared to traditional descriptors. We have conducted 3 types of experiments to investigate different traits of our approach. In the first one, ours was compared against SHOT and M2DP with regard to top K accuracy. The figure shown in this slide showcases all results in all planetary sequences. Our approach generally shows most accurate and stable compared to existing works. The second experiment focused on robustness against random noise. In this experiment, we add uniform noise to each point location. As shown in this figure, our approach showed no noticeable accuracy degradation with small or medium scale of noises. The third experiment investigated the robustness regarding different downsample sizes. The result is illustrated in the right figure. Our approach was the most inverse proportional to the point cloud density. This result was very natural, considering the sampling theory. Therefore, it is crucial to select an appropriate grid size depending on the property of the environment. We tested our method's traversability analysis in one of planetary scenes, including hazardous regions. As shown in this figure, the robot recognizes the hazardous areas with degrees of the danger. We built a cost map from these masks that safely navigated the robots to the desired place. As a conclusion, we propose structural discrete Fourier transform for informative place description and traceability analysis. We demonstrate the high performance of the proposed method in unstructured and urban environments, where it exhibits superiority over baseline. Furthermore, unlike existing descriptors, the proposed method simultaneously analyzes traversability based on the physical property of the ground. Thank you for your listening.